stowed position with the astronaut equivalent robot stows back down for storage. Well, here are the instruments that we put onto it. Of course, we have high definition television in stereo. Gives you the feeling of being there. We do have navigation cameras pointing all 4 directions. So when you're looking for where do I go next, you have cameras that are looking in all directions. Hyperspectral infrared, this is a science camera, gives you mineralogy just by looking. Rock abrasion tool, a rock hammer. Realistically, that may end up being the pneumatic chisel. It might not be the best solution to actually pick up a hammer in the manipulators, although it kind of looks good in the pictures. Rock drill to go deep into the rock, microscopic imager, alpha proton X-ray spectrometer for in situ sample analysis, and arms and hands and sample collection. The robots are carried themselves on what we originally called the pickup truck and eventually just got called the truck. When you zoom in, you can see how they fit into the truck, and the truck has articulated wheels carried around. The idea is that the human equivalent robots are good over rough terrain, but they're not designed to go hundreds of kilometers. They're designed to explore an area at essentially a walking pace. But after a while, you have a 500-day mission, a year and a half at one site. You get bored with a walking pace and say, well, let's get in the pickup truck, let's drive somewhere else. So you drive somewhere else. They contain the main power system. They have the solar array, which recharges the rock arms. So the rock arms come back to the pickup truck at night and recharge. That allows them to have high power, but not carry around solar arrays. They do have some primary science, particularly drilling. We've decided we wanted to be able to do a sample return, but in fact we weren't able to finish that with the time that we had in this particular study. So we don't have a sample return rocket in this study. But here shows the advantage of the articulated leg. Here we have the down and driving position, but when we want the rovers to drive on and off, or when we want to do the drilling, it's essentially a stationary flat platform. This shows it in drilling or rockhound deployment position with the legs in the up position. A couple of other things not really shown, a dipole antenna for ground penetrating radar. So as we drive over, we can see what is below the ground. That idea that the legs themselves are articulated is not new with this project. Here's just a couple of the robots that have been designed mostly at JPL with legs that can be articulated and changed in position. Here shows the Go4 rover with the legs kind of down, putting the rover up, and then here's the legs lowered a little bit, lowering the center of gravity. Just showing the dimensions, the truck actually is pretty big. It's 5.2 meters. It is pickup truck size. And as it turns out, the solar array is huge. That's a 5-meter diameter solar array. It needs to be able to charge the rovers overnight, pretty much every night, even in worst case conditions. We did do the quick analysis, by the way, to see whether the wind would turn over the solar array if it got to be a very windy day on Mars, and it doesn't, but we did check that out. Here's the top view, we're looking at it. It can be pretty big. It folds in a little bit less. The chassis itself is 2.5 meters, a pretty small chassis. Say again?
You said it carries 6?
It carries 2 of the robots. So there's actually a total of 6 robots, but we're at 3 sites at once. On the carrier vehicle, we have a bunch of instruments. I somehow neglected the ground penetrating radar. That actually comes in under the communication system technically. But among other things, note that we have a winch and a cable so that as needed we can winch the robots, for example, down cliffs. A lot of the very interesting sites on Mars are sites that are down a very steep cliff. These are the sites where we look at transient liquid water. We want to be able to put the robots, essentially repel them down the cliff. This shows the truck with the rockhound rovers. As it gets stowed up, everything folds in folds down and fits into an aeroshell. So this shows everything folded up so that we can enter the atmosphere in the aeroshell. Sort of top view showing how everything folds away. Pretty big aeroshell, 4.5 meters. I was going to show that a little bit later. But in fact, that's the MSL aeroshell. We fit into an existing aeroshell, which we hope will be demonstrated with a launch in a year next October. We did mass, fuel, cost, energy, and data volume analyses. I do want to talk a little bit about mass growth. It turns out some very hard-won experience shows that the actual mission mass is higher than you planned. And there is a set of rules that say how much of a budget you need to keep in order to make sure that when you actually build it and it comes in heavier than you planned, it still comes in light enough that you can still fly it. And this is just a typical graph of showing that mass growth. This is what we call the mass growth allowance. Then we have some margin. And then actually the customer keeps a reserve. The customer says, well, if your rocket can launch, say, 10,000 kilograms, we want to see your system come in at 9.5 thousand kilograms, and they keep that reserve. So these are the various reserves. But no, we're keeping a 30% mass growth margin in the system. The amount that you allow, the amount by which you assume that what you actually build will be heavier than what you planned, depends on how far you are down the system and what the system is. But when you are just estimating, and we're at the estimation, if we don't have physical objects that we can pick up and say, here's a flight unit, here's how much it weighs. For structures, we carry about 18%. For wire harnesses, actually 50%. So various mass growth estimates depend on how much difference there is between paper and actual mass. If you actually measure it, you can pick it up and say, I just weighed the one that we're going to fly, it weighs 1 kilogram. There's no mass growth allowance. You actually weighed it. Existing hardware that isn't your actual flight mass, there's a pretty small mass growth allowance. So we kept these mass growth allowances. So when I show masses, landed masses, these are masses including the mass growth expecting. So these are the numbers. The Rockhounds come in about 350 kilograms for 2 of them, about 175 kilograms each. The truck itself, 815. The landing system, the aeroshell and the skyhook, 2.4 tons. This is based on the Mars Science Laboratory. So the whole system comes in at 35,065 kilograms. The Atlas launch capability is 5,000, so we're well within the launch capability of the Atlas. The Mars Science Laboratory is an entry mass of 3.257 kilograms, 3.2 metric tons. So actually we're about 9.5% above the MSL entry mass. So pretty much this fits inside the MSL system. I'm assuming that we can scale up by 10%. It actually fits inside the volume perfectly. And this is that Mars Science Laboratory. This is the actual one that we're going to send to Mars 1 year from October. You can see how big it is. These are some of the technicians working on it. This will be the biggest entry vehicle ever flown. It is bigger than Apollo Castle. And it's going to Mars this October. Wait for it. And this shows how we deploy. We're inside the aeroshell. We deploy the wheels out. And then we can remove the back shell as we're coming in on parachute. This is a land on wheels concept, very similar to the Mars Science Laboratory. This is the orbit we ended up in for teleoperations. We spend a lot of time at the team doing orbital analysis, trying to pick which orbit can see which sites for how long. It's an odd orbit. It's a little bit cheated ahead. It's a 12-hour Molniya orbit. A 12-hour orbit with Mars going around every 24 hours. Actually, it's a 12-hour and 20-minute orbit. Mars moves around every 24 hours, so that means that you hang in the sky at the periapsis for about 16 hours in the Mars day, then you come by, whip by the apoapsis and come out for 16 hours. So you can do a long science shift visible on this part of the planet, and we have picked this particular orbit such that it precesses around the planet in a Mars year so that the apoapsis stays above the sites on Mars that you want to do your operations at. We picked 3 sites on Mars, so you can have 2 shifts, 2 astronaut geologists at one site, 2 astronaut geologists at another site, and then we also have 2 crew members that are doing the pilot and supporting. So we can support 2 sites a day. We also have a great deal of interest in polar landing sites. We happen to pick the South Polar region for interest, although after listening to Carol Stoker's talk this morning, I think, well, maybe we should have picked the North Polar regions. They're both interesting. We could have done either. But we're hanging, we picked our orbit so that we are inclined. So we do see the South Pole. Much of the time, the South Pole is dark. So in fact, our 3rd landing site, the South Polar region, we're operating at only during the Martian summer in the South Polar region. Here's the crew control and transfer vehicle, the CCTV. Has a lot of tanks. This part is actually the habitat, right here, an inflatable habitat. When we do our trans-Mars injection, we can drop that tank. Sort of interesting, we're dropping the tanks from the front instead of from the back. That's sort of an odd thing. Why are we doing that? Why aren't we doing what most rockets do and sort of drop off the back end? Well, that's because we're also using our vehicle for artificial gravity. So the heavy rocket engines, the remaining tanks for the trans-Earth injection, all allow us to rotate. We're spinning at 2.5 RPM. That gives us 0.875 gravities, just a little bit less than 1 Earth G. Here's our inflatable habitat, and there's the actual, we used a constellation module for a crew return vehicle. Here's all of the data. Hold on to your hats when you see what the mass is. 470,000 kilograms. These long duration habitats in space are pretty heavy. This thing holds human beings for about, what is it, 18 months on Mars, 9 months each way. It's a little bit over 3 years that they're living inside the habitat. They get pretty big. Comparing it to the Mars Design Reference Mission, what you can see is we're getting pretty close to the science that you get out of 3 human missions to Mars. We can do 3 sites separated a long way away, and a site is 100 kilometers. That's as far as your humans could explore in their pressurized rover. We can do 30 science sites explored per region. It turns out the human mission can do at most about 14 science sites because it takes about 2 weeks due to traverses to do a science site. A human, based on actual numbers, it takes about an hour a day to suit up and desuit, and about 20% of the time spent on an EVA is just moving around, not doing science. So you get about 4.8 hours of exploration in an 8-hour shift inside your spacesuit. But we can get 8 hours of exploration because the robots don't have to suit up and suit down. In order to start the exploration, you sit down in your telerobotic station, you turn on your computer, and you say, I'm ready to go. Mars mission had 4 geologists on the surface, plus 2 astronaut pilots for support. We're exactly the same. Science sites have to be within a rover drive of a high safety landing spot. We're exactly the same. We have to be within driving of a safe landing site. But if we blow the landing, we don't kill anybody.